cherry, pick up 2. But although it is marked as a hard problem, but we will relate it with a medium and a medium, like medium and a medium easy problem, and then from that it will be very easy for you. Let's start off what the problem says. The problem simply says that we are given a rows cross columns matrix, which means a m cross n matrix called as grid, and it represents the field of cherries, where grid of I comma j represents the number of cherries that he can collect from I comma j cell. Okay, so every cell of that matrix has some number of cherries, and you can collect those cherries. Now you have two robots that can collect cherries for you. Robot 1, it starts off from the top left corner, which is 0 comma 0, because if you have a matrix, this is the top left corner, which is 0 comma 0, and robot 2 starts from the top right corner, which is 0 comma n minus 1. If the columns are n, so you can say n minus 1 is the number of columns. Now we have to return again both the robots will keep on moving, and again make sure that both robots should reach the super end of the grid. Any of the robots cannot stop. At every time, every robot will go one level down, and they are saying that, what is they have saying? They have said that a robot, if it is at a cell I comma j, then the possible options for him to move at the next iteration is I plus 1 comma j minus 1, I plus 1 comma j, I plus 1 comma j plus 1. Or you can indirectly say that if I have a grid, a robot is, let's say, at this specific cell I comma j, then in this step he will have to go on to the next cell, which is I plus 1, I plus 1, I plus 1. So for sure he has to go on to the next step, which is I plus 1, which is the next row he has to go on. And for the next column, he has three options. Either if he is at the column j, he can remain at the column j, as you can see, he can remain at the column j, he can go to column j minus 1, or he can go to column j plus 1. So we can easily visualize that if I am at this specific cell, I can go to this and this. Just next left cell, next right cell, next down cell, and all of them should be one step down to me. And we have to ultimately return the maximum number of cherries which we can collect. We, as in two robots combined, can collect for us maximum number of cherries. And also this just say that when any robot picks and pass through a cherry, it picks all the cherries and the cell becomes a 0, which means he will just pick off all the cherries, which means we can pick a cherry exactly once. That's what it means. Next thing is very important. When both the robots stay in the same cell, only one takes that cherries. For it is very obvious that, okay, both the robots are kind of moving like this, down, left, down, and all that stuff. So for sure there will be a point, let's say here it comes, then here it comes, here, and it comes here. So for sure there can be a point where both the robots can collide. And again, both the robots are smart, and you know that if at this specific cell I had 4 cherries, so only like in total combined someone can pick only 4 cherries, because I have at max 4 cherries. So this says one thing, that if you have 4 cherries, you can only take in 4 cherries. That's it. And ultimately you are not concerned about what robot 1 takes, what robot 2 takes. Ultimately you are concerned about what, again, both the robots are your robots. So you just want maximum number of cherries to be picked, not considering what robot 1 will pick or what robot 2 will pick. That's it. Make sure, this will confuse many of you, that you will be concerned about, okay, what I should make robot 1 pick. Nah, don't think about that terms, because you know maximum number of cherries and both are your robots. That's it. Last is that for sure robots cannot move outside the grid, and last is robot could reach the bottom of the grid. Only then I will say, okay, now I should say what all have my robots grabbed. So you can for sure see with this specific example, this is robot 1 which is in green, robot 2 which is in blue. So he will make like this, down, then right, and then down. This is what robot 1 will collect. Robot 2 will collect like this, like this. So in total, robot gave me 24 as my number of cherries. Now, considering that we had two robots here, let's forget that for now. We consider that if you had only one robot, and if I would have asked you, imagine, like, okay, just imagine you have only one robot and everything remains exactly same. The operations required are from I comma j, you can move to I plus 1 comma j plus 1, I plus 1 comma j, I plus 1 comma j minus 1, and also to super n. Robot one, again remember, you have only one robot, because we have to break the problem down to what we have seen earlier, what problem we have seen earlier. So we'll just simply say, okay Aryan, I cannot try greedy, because for sure if I might end up trying greedy, which means let's say if I have a 3 here, I could have moved to a 5 here, but let's say I don't move to a 5 because greedily thinking I would have moved to a 5, let's say. But okay, let's change the value. Let's say here it is a 5, here it is a 2, right? Now from this 2, let's say this value would have been a very big value, which is 15. That's it. So it is more than sufficient to prove that greedy would not work, because we would have been had here. So greedily would have moved to 5. Now would have been 1. You could have moved here, moved here. So this would have been, let's go 3, 5, 1 and 2. You would have not gone greedily and would have tried for all the possibilities. 15 and then 2, 1. For sure, in future, if I get some big value, that's not sure. So I have to try for all the possibilities. So one thing is for sure that I cannot go greedily in these kind of problems, and I have to try on for all the possibilities. Now, try on for all the possibilities is simple. Try on for all the possibilities. Initially, my robot, again, remember, I have only one robot. My robot was at the cell 0, 0. He has 3 options. He can go like this, and like this. Which means left down, right down. So again, left down he cannot move because it is out of the way. That we can handle with some if conditions, that okay, if your cell I comma j, all that stuff, if it goes out of bound, just simply make sure that you return something. But that we can handle in the edge cases and stuff. But the actual case is okay, or here. So he will have 2 options. Again, we will plot both the options differently. One option was landing at the cell right here. The other option was landing at the cell right here, which is 1, 1. Now again, he has 3 options. Again, whenever I say he land onto a cell, remember this cell. So what? So all changes he might had, he will grab those at that grid location, j, he will his result. And remember, he has to maximize his result because you want to number of cherries. So again, and try. Okay, for children, I will go to my next cell plus 1. Again, I have written DFS or solve. So it is simply saying, okay, I will try recursion. But what I will try with my recursion, I will go on to my next cell, which is I plus 1. Go on and try for all the possible columns. As you have remembered, my columns are 3 possibilities. Plus 1. I will try on for all these 3 values for my column for this specific I plus 1 row. And whatever maximum I would get from my recursion, I will simply add in my current answer. So that is how I can simply get maximum number of cherries. Now simply let's try run much more further, but yeah, that is how our answer would look like, or our code would look like for one robot. Remember, now if you were at this specific cell, again you have 2 options, although you had 3 options, which is left also, but you cannot go left, so you know that you will have only 2 options. So he will go on 2, 0 and 2, 1. And same way, if you were at 1, 1, you have 3 options, either this cell, or this cell. So you will go on to 2, 0, 2, 1 and 2, 2. Now again, if you had seen so far, so you will simply add while what's up for, like, obviously you were at 0, 0. Now you would have asked for 1, all these possible j values. As you can see, 1, 0 and 1, 1 you would have asked for, although you would have asked for 0, 0, but -1 would never as a column will occur. So you would have tried for 0, 1. As you can see, 0, 0 and 1 you would have tried for it, which means 1, 0 and 1, 1 you would have tried for. When you will try for something, then it will go on and count for its its own recursion. Then you will simply add its corresponding cell values, which means you will count grid of 1, 0, and then again call for recursion. Again, in the other case, you can have grid of 1, 1, and then again call for recursion. You can see simply this will also count, and this will again call for recursion, all that stuff. So you can see you are calling for recursion with the same cell, and 2, 1, or 2, 1. Oh, and again the same recursive tree will be made for this specific cell and this specific cell. Same recursive tree will be made for this cell and this cell. So you know, oh, in one robot itself, I know to find the maximum number of cherries, I will have repeating sub-problems. So for sure, I will have to apply or do the memoization with my DP. That is for sure. And we are using 2 robots, so for sure, 2 robots is much more complex than 1 robot. Then we will again have repeating sub-problems, so we will always make sure that we will apply memoization in that 2 robots also. But we got a glance of how the problem or how the answer would look like. Now coming on back to a main problem when we had 2 robots. Now make sure one thing, that both the robots coincide, please take only that number of cherries, which means only one robot will take the cherries, other robot will go empty-handed. So make sure that part. Now we'll start off with the same problem. Again, because of one robot, now we have a background of how the recursion tree will look like. We know for sure that we have to apply DP, and we know that okay, how the base cases and stuff will look like. And probably we'll also know that how the recursive state, because if you have gone back, it is simple. You will add simply grid of I, j, and then you will try on for all the possible values. Like same recursive next row and then possible j values you will try on. The same way we will do in for 2 robots. Now we have a robot 1 and robot 2. Now simply go on and try for. So you will see robot 1. If I bifurcate it down, which means let's say if I bifurcate and imagine robot 1 will move individually, robot 2 will move individually. So if robot 1 would have been there, it would have gone to the below cell or the below right cell. Okay, below cell is here, below right cell is here. And for same for robot 2, it would have gone to below left cell and below down cell. So this is below left cell, this is below down cell. Now again the same way, Aryan, hold on. You took one robot. Where did the other robot go? In a grid, 2 robots should be there. Where did you miss? Where is the robot 1 here? So that is we are doing something wrong. We have to put in both the robot possibilities. So you know that robot 1 can move either down or down right. Robot 2 can move either down or down left. So I can say that if I have to move one possibility, so one possibility can be robot 1, again one possibility can be robot 1 moved down and robot 2 moved down left. Other possibility can be robot 1 moved down, robot 2 moved down itself. Other possibility can be robot 1 moved down right, robot 2 moved down left. Other possibility can be robot 1 moved down right, robot 2 moved down. So that can be the 4 possibilities. But Aryan, how we would know we had 4 possibilities? See, as simple as that. First robot will have 3 options to move on. Second robot will again have 3 options to move on. Right? If he has 3 options, so for sure, if some I, j is here, I will see corresponding. I will have 3 options for my robot 2. For this also I have 3 options for my robot 2. For this also I have 3 options for my robot 2. So for 3 options for robot 1 movement, I have 3 corresponding options for robot 2 movement. In total, I will have 9 options for my robot 1, robot 2 movement. That's it. So in this you can see, although you had only 4 options, why is that the case? Because this edge case got removed because of it was out of my matrix. But it is simple. Robot 1 had 2 movements, 2 possible movements. Robot 2 had 2 possible movements. So in total I have 4 possible movements, and that is how it will look like. That robot 1, robot 2 here, robot 1, robot 2 here, robot 1, robot 2 here, and robot 1, robot 2 here. And that's how, again, if you remember in the very basic example, we knew that we had these 3 possible movements at every step. Which means in my recursion tree, I will have 3 children at max. Now in my new recursion tree, I will have 9 children at max. Right? Now let's simply see how you will write the code for it. Exactly same. So you saw that earlier for the simple recursion, if you had gone back, just let me quickly go back. In the simple recursion, you had only I and j. That was more than sufficient for you because you had only one robot. But as you have now two robots, so you will have robot 1i, robot 1j, robot 2i, and robot 2j. Now you can simply go and apply your simple recursion. But if you, again, I have not even written the code, but with seeing this recursive state itself, and I know I will have to memorize my I and j itself, because in the above smaller example, we saw that you have to memorize I and j because you have a repeating subproblem of I and j, as I said. Then for sure I will have to memorize R1i, R1j, and R2i and R2j. So for sure, if I have to memorize this, which means for sure, hands down, my time complexity will at least be n into m, m into n. Let's say m is the number of rows, n is the number of columns, multiplied by m into n. So m into n whole square, or I can say m square into n square, will for sure be time complexity. It can be more depending upon if we apply some more loops inside this recursion, but it will for sure be this. So can we optimize it right here, right now? Can we optimize it? Yeah, we can. How? Because you will see how, like, firstly, how you even think of memorizing or basically improving something, which means you have to right now memorize, like you have to right now optimize it. If you have to optimize something right now, you will see, okay, can I reduce this? Which means if you want to reduce this, you will have to reduce these states, or basically either you reduce this states right here, or you can take these states, but the memorized state, which means the states which you will actually memorize, you will have to reduce those. So can we figure out a pattern? Oh yeah, if you remembered, there was a very stressful thing in the beginning I told, as in like I gave a stress in that thing. It was that at every step you are going on to next row, which means for both the robots, their row will be same. For both the robots, their R1i and R2i will be same. Both the robots will be at the same row at every step. That is the thing which we can utilize to remove one of the robot i's, and thus we will remove one of the m from the entire thing, which means one row factor in a time and space both have been reduced because of this small optimization which we have done right here. So instead of robot 1i, robot 2i, I will just only keep I itself, because I know both robot 1 and robot 2 will have the same I, and then I will have a robot 1j because it can be different, and robot 2j. Now, a simple base case is, as we can simply see, that my robot should not go out of my matrix, and if it is going out of my matrix, I have to return something. Now, to return what defines that ultimately my answer wants what? My answer wants maximum number of cherries. Now, if something has gone out of my matrix, minimum of cherries which is here is 0. So, if something goes out of my matrix, out of my grid, I will return 0 number of cherries for him to add, because I want in my answer to add maximum number of cherries. So ultimately maximum, which means if something is out of my matrix or out of my grid or basically invalid, simply return 0 because it will not impact my answer. Thus, if I have reached the super end, which means my I has gone out of the grid, then simply return a 0, or if my j has gone out of the grid, simply return a 0. That's a simple base case which you can have. Now, Aryan, that was a base case, but how's the actual case going on? If you remembered, in the above case, if you remembered, in the above case, we simply added the grid of I comma j, because we imagine we had only one robot, and that will actually we will add the number of cherries in that specific robot. But here we have two robots, so for sure, for the first robot, I will add the number of cherries, which means grid of I comma R1j. For the second robot also, I will have to add the number of cherries. Again, I remembered that both will be on the same row, but can be on the different column. So R2j. I will add the corresponding number of cherries in my result. Result is my final number of cherries, maximum number of cherries which I can have in my answer. That I will add, that is okay. But if you remember, there was one condition I again stressed on very much. What was that? It was the condition that both the robots, when both the robots stay in the same cell, only one can take the number of cherries. So I can add a simple condition in this, is that Again, I know the I is always same. So to make sure the robots are not on the same cell, I will make sure if my R1j is not equals to my R2j, which means both the robots are on the different cells. You should add their you should actually add the R2j corresponding cell number of cherries also in your result. If they are on the same cell, you have already counted, please don't count that cherry again, because from one cell you can take only number of cherries. So that will be our actual case. But Aryan, where's the recursive code gone? No worries. You can actually, again, this is the cherries which you have gotten from the current cell. But as a recursion, you will go and ask for the maximum number of cherries which you can get from the children. And if you have remembered, we will get at max 9 children. So I will go and ask for solve of I plus 1. But now my x and y will be there. Again, if you had remembered, our base case was, like our actual case was R1j and R2j. Saying, okay, the corresponding column of robot 1 and the corresponding column for robot 2. So x, my corresponding column for robot 1, it can either, again, if you have to remember, he can either go to R1j minus 1, R1j, R1j plus 1, and same for robot 2, he can move to R2j minus 1, R2j and R2j plus 1. But if you remember, I have to move both the robots 1 and robot 2. So my one possibility can be R1j minus 1, R2j, R2j minus 1. Next possibility can be R1j minus 1, R2j. Next possibility can be R1j minus 1, R2j plus 1. Next possibility can be R1j, R2j minus 1. Next possibility can be R1j, R2j. Next possibility can be R1j, R2j plus 1. This is how 9 possible pairs I can form, which means at every level, for every cell, I will have 9 possible pairs, and out of all of them, I want the maximum cherry sum which my child can give me. I will get that specific cherry sum. Same, which we did for one robot. In one robot, we just have 3 options, and from that we are grabbing the maximum cherry. Here we have 9. We'll just grab the maximum cherry from it, and then we can simply add that maximum cherry in this specific result. See the code? It's pretty simple. Let's see the recursive code. Exactly same. That. Firstly, we will have our I, we will have our R1j, and we will have our R2j. Very beginning, if you remember, you will start your robot 1 from cell 0, 0, and you will start your robot 2 from cell 0, n minus 1. This is showing the starting cell. So I've named I as I itself. This is my R1j, robot 1j, and this is my robot 2j. Now, simple base cases, if anything goes out of my matrix, simply return a 0. Now, if you had remembered, if I am at a specific row, then simply count the corresponding number of the cherries which you can have. So for this specific I, R1j, I will add the corresponding number of cherries, and I will also make sure if my R1j is not equal to R2j, which means both the cells are different, I will simply add the I, R2j number of cherries also to my result. But this is the simple result. You have to go and ask the recursion for the maximum answer, maximum number of cherries which you can get in from the sub problems, as in from my child. So I'll go and try for all the possibility as I have showed. We have 9 possible options starting from R1j minus 1 to R1j plus 1, which means R1j minus 1, R1j and R1j plus 1. Same for R2j minus 1, R2j and R2j plus 1. I will form 9 possible combinations, and I will just go and ask maximum for the next row. What's the maximum I can get? Okay, get that maximum, which means improvise that, keep on improvising that maximum value, and keep on going and asking your recursion to solve it for the next row with this specific x and y cell. Again, these can be the 9 possible options. And with this, I will simply, again, in the existing result, whatsoever my child has given me, I will add that in my result and can simply return my result. But we know it's a simple recursion, and we know that we can actually memorize it. So we'll just simply add 2 lines of code. We will initialize our DP. Again, the memorization vector, I named it as a DP, and I initialized my DP saying DP is nothing but of size m, n and n. This is for I, this is for R1j, and this is for R2j. This is how I initialize my DP with the default value of -1. And then while going on inside my recursion, I just checked, okay, if I, R1j, R2j, if it's not equal to -1, simply return that value. And before just returning, please assign this value. With this, you can easily see that my time complexity has reduced to m, n, and n, and this is this is a 9. So you can say my time complexity is actually O of m into n square into 9, but 9 is a constant factor, so you can actually remove it. So this is your time complexity, and the same way your space is also O of m into n square. Again, remember the fact that you have optimized the space by a factor of n while generating this answer itself, although that will also pass, which means m square into n square will also pass, but still you optimized that, and ultimately you have reached to that m into n whole square as both time and space, and that's why you can simply solve it. Cool, thanks everyone. Goodbye, take care, bye.